I'm trusting your calculator skills there. Can I get a second? Any 1 second? Not that I don't trust you, but I always like to have at least 2 people confirm. It's not that I don't trust you. It's I don't trust you. Sure. Yeah. It's less than 2, greater than 1. Yeah, yeah. I don't know. I don't have memorized. So, yeah, no. Yes, okay, so that's it. So that means if I were to be standing on that surface at that point up there, pointing in that direction, and take a step, I'm going to be going up, right? Now, if I turn around and go the opposite direction, what do you think is going to happen? If I turn around like 180 degrees? It's going to go down because, you know, if you're going up this way and you turn around, you're going to have to go down. So, all right. Questions?
If you draw the triangle, could you draw a triangle just for my question?
You want me to just draw a triangle?
A random triangle. And then for your height, for 1. All right, triangle.
Oh, okay. That's a spherical triangle. It's a triangle on a sphere. We'll talk about that later. So you mean like a Euclidean 2-dimensional triangle, like this? I'm being a smartass, I'm sorry.
When I think of sine of 30 degrees, I think 1/2, and then I put 1 for the height, 2 for the hypotenuse.
Mm-hmm.
And then you can put √3 for the x.
Yes, you could do like a right triangle like this and then say 1 and 2 and then √3. Is that what you're saying?
Components, could you do √3 and then 1 instead of √3 over 2 and 1/2? Is that still a unit length?
Could you use what instead?
Saying to multiply everything by 2, basically.
Could you use √3 and 1 as your u? No, that would not work. No, because this is not a unit vector. Yep. So what you have to have, yeah, your hypotenuse would have to be 1. But what you could do real easily to fix that is just find the length of this vector. So, you know, find its length. Take the square root of each of these pieces squared. So square that, you get 3. Square that, you get 1. Square root of 4 is 2. And just divide each by 2. And now you have a unit. Well, that's what we had before, yes. So you would be off by a factor of 2 had you not normalized it and made it unit length. Got it? Okay, let's look at the next one. Or the next idea here. I shouldn't have been a smartass, I'm sorry. But it's interesting, you know, spherical triangles don't have the same properties that the ones we're used to have. All right, so z is equal to f of x is equal to natural log of x squared plus y squared. Find the directional derivative at the point 2, 1. In the direction of the vector u is 1, negative 2. So this is a little different in this problem because in the last one, told you that we gave you the direction by giving you an angle and how that angle was relative to the x-axis, right? This one, you're not given an angle. You're actually just given a direction vector, right? So I'm going to go back. I'm going to draw the domain again. The point that I'm at is 2, 1. The direction vector, which is completely separate from the point, right, has nothing to do with the point, is the vector negative 1, 2. Can y'all see the surface above this? Can y'all see the surface that's above this thing? And we're up at a point on this, and we just want to be on this surface pointed parallel to that red vector, right? And then you just turn the whole thing over, and now we're, you know, the surface is up. Okay. So we need a couple of things: partial derivatives, which we should be able to take, right? And we need to figure out what our u is. U is given to us, or is it? It's not. It's not a unit vector. So we can't call that the u. Even though I called it u here, I'm trying to trick you. all right? So this is not a unit vector. So I'm going to call a new vector v, that u vector divided by its own length. And then what I'm going to do is in my formula, I'm going to use directional vector, directional derivative in the direction of v, because v will be a unit vector. So we just take the vector u and then divide it by its own length. What is the length of u? Square root of 5, right? So I'm just going to divide it by its own length. But that just means you divide each of the components. And that's it. Yes, you could rationalize, but I'm just going to leave it like that. So this is a and b. We agree with that? All right, so I need some partials. Let me get some partials right now before I start putting this all together. Partial with respect to x. 2x over x squared plus y squared. So derivative natural log something is 1 over it, and then, okay, partial with respect to y is 2y over x squared plus y squared. There we go. And now I'm ready to put it all together. So I'm kind of going a little quicker here with these partials because that's now in the past, okay? The directional derivative in the direction of v of the function at some point xy should be a, right? So negative 1 over root 5 times the partial with respect to x, which is this, 2x over x squared plus y squared, and then plus b, which is 2 over root 5, and then the partial of f with respect to y. Is it doing that again? I hear that every single time. See, I've got the magic stick. Is that what we called it last time? All right, so that's it. That's our formula, right? And then now we just need to plug in 2, 1, and we're done. So let's plug in 2, 1. Are there any questions? Does this seem straightforward? Yes? No? For now, I mean, we don't want to make this more complicated. The only thing that's going to get complicated perhaps in the homework is maybe these partials are going to suck a little bit. We haven't talked about yet, what happens if we have like a function of 3 variables. Like, can we still do a directional derivative? Does it even make sense? So we'll talk about that in a second. All right, what happens when I plug in 2, 1 for this right here? 4 over 5, 4/5. And then when I plug in 2, 1 on this one, what do I get? 2/5. And then adding these, they have the same denominator, don't they? Uh-oh.
Yeah, I got 0.
It's got 0. Did we mess up? This is a number. It's not a vector. What does that mean? Flat. You're flat. So you're standing, and you might possibly be at the top of like a hill, or possibly the bottom of a hill, or neither one. It could be a saddle point. It could be a lot of different things, okay? Because the surfaces are complicated. It's not as simple as, back in Cal 1, your derivative in Cal 1, right? If the derivative was 0, you were either like here, right? Or you were here. Or you could possibly have had something like this happen there, like this, right? Like that was pretty much it in Cal 1 when the derivative was 0. You were either at the top, at the bottom, or at one of these weird points like this where you're neither the top nor the bottom. This is kind of like what a saddle point is for us, which is later. But it can be even more complicated with surfaces. So it's okay to have a derivative of 0. The next section, in fact, the next section is about trying to find the maximums and minimums of a function of two variables. It's a method, it's a procedure on how we do find the highest and lowest points on surfaces. And do you remember, like in Cal 1, we had like the first derivative test and the second derivative test? We have something like that for surfaces also. And then we say, hey, we can do a pretty good job with that. And then we get into the next section, which is 11.8, which is called Lagrange multipliers. And that's an even more specialized version of finding maximums and minimums. And that problem is, that section is kind of tough. But your test is a week from this upcoming Monday, right? Your midterm is a week after that. So we will have, next class we'll do 11.7, okay? And then we will, on Wednesday, do more 11.7, start 11.8. Then the following Monday will be your test. It'll only cover up through 11.7. I'm not going to test you on 11.8 until the final. All right? And maybe next Wednesday we'll have some time to talk about the midterm. Making a midterm is kind of hard because we have a lot of information, right? So how do I pick something that's going to fit in an hour, 40 minutes? I don't know. I guess that's the pleasure I get to have, is trying to pick something to fit in an hour, 40 minutes. And you have the pleasure of preparing for something that is going to be an hour and 40 minutes and can cover, almost 8 weeks of class. So it's a good thing. It's a good exercise because a lot of times as you get higher in your education, there's going to be less tests. It's going to be more like midterm final. I took plenty of classes where my grade was 50% midterm, 50% final, and for an hour 40 minutes you had to walk in there and perform, and you had to be ready for it. There wasn't any after the test like, hey, can we do corrections, or like, can you curve us? Like, no, this is all grown up now. Okay, you just have to be prepared for that test. So, okay, we're done. This one. All right. So now we define something. We define what's called the gradient vector. This gradient vector is going to become very important to us as we proceed through this this chapter, and we'll see it again later on too. This is supposed to be a dot product. I don't know why that looks like that, but remember that this is the definition of the directional derivative, which is what I wrote up there on the board. If I were to create two vectors, a vector that the first component was the partial of f with respect to x, and the second component was this, and I dot that with the vector AB, then wouldn't this be equal to this formula right here? Because when you dot product, don't you do this times this plus this times this? Isn't that what you do when you do a dot product? I know it's been a while since we did dot products, but dot product was easier than cross product. So this right here is another way of writing the directional derivative, isn't it? And so this right here, we knew that this was the directional derivative, right? That was directional vector. That was the vector that told us which way to point, right? This we've never really seen before. We've never actually put the partials together into a vector, have we? Never. But now we are. We're going to put the two partials into a vector, and that vector is called the gradient vector. This right here is called the gradient vector. But this note is just to make you aware of the fact that you could rewrite this formula as a dot product. The next note is where we define the gradient vector. So the gradient vector is defined as follows, and that's what I wrote right here. This is, you've seen the delta before, right? Delta x, change in x, right? You've seen that before. Flip that delta over. That's the symbol we use for the gradient. For the gradient. And it's actually, this symbol is called del, okay? It's called del, which is also what I told you this symbol is called for the partial derivative. So same name for two different symbols. It's confusing, I understand. So del F, you'll hear me say del F, and that's what I'm referring to, all right? So just remember that the gradient vector is exactly that. It is a vector, and it's just made up of partial derivatives. That's all it is. Gradient vector is just a vector with the components being partial derivatives. So simple example, find the gradient vector. So this is one of those problems like someone who's never even ever seen calculus 3 or anything like that or any of this vector, they look at that, they're like, man, that looks hard. What's a gradient vector? It's nothing. It's really not much. It's just a couple of partial derivatives, right? Well, you know what I'm saying? It's not like, this is not going to be a 3-page problem. This is just an exercise in partial derivatives. That's all it is. So the gradient vector is this, right? And so let's just compute what's the partial of f with respect to x. Let's see. So what is the, we have a sum, right? So we can do partial of e to the x y with respect to x would be y e to the x y. See, I'm assuming that you're okay with that by now, all right? That you can do partial derivatives by now. Plus derivative cosine of x plus y. What's the partial of that with respect to x? Negative sine x plus y. Anything else there? That's it? Okay, I agree. And then now we do comma. So the second component of the gradient vector is the partial of that with respect to y. So it's instead of y e to the xy, it's x e to the xy. And then minus, this part's exactly the same. Okay, so if you are still at a point right now where this is like, what the heck's going on? Well, you've got work to do this weekend then. I think the take-home that I gave you, the partials get a little complicated because there's some product rule in there that you have to keep track of, and that's it. That's the gradient vector. Congratulations. All right. Now we're going to see the gradient vector is extremely important. We're going to see its value in a little while, but before we get to why it's so important, let's extend everything now. You know, everything we've been doing so far, it's been f as a function of two variables, x and y. And so we were looking at it as a surface. The domain was down on the ground, right, in two-dimensional space. But hey, what about if we have a function of 3 variables, f of x, y, z? Now your domain lives where? Where's your domain? The domain's in R3, right? Let's say someone gives you a unit vector in R3, which would be a direction to point in 3-dimensional space. Then